Every year, the world produces over 1,200,000,000 wool products. Sweaters, scarves, coats, all made from a material that's remained essential in the textile industry for thousands of years. But what makes ordinary sheep's wool so special? Behind every warm sweater lies a process where nature meets cutting-edge technology. From shearing sheep to finished fabric, wool undergoes an incredible transformation. How does a clump of dirty fleece become an $80 billion a year industry? Stick around to the end and you'll discover how an industry turns nature's gift into the foundation of global fashion. The wool industry is a massive machine that processes over 4 billion pounds of wool every year. That's nearly 2 million tons. 3 countries control more than 60% of global production: Australia, China, and New Zealand. Australian farms specialize in fine, high-quality merino wool, which commands the highest prices. China, meanwhile, is the biggest processor and consumer. Thousands of textile factories there transform raw fiber into finished products. The economic value of the entire wool industry tops $80 billion annually, including exports of raw fiber and finished goods. But wool's biggest advantage? It's a completely renewable natural material. Sheep grow new fleece every year, making this one of the most eco-friendly industries in the fashion world. The journey of wool begins on the endless pastures of New Zealand and Australia, where farmers manage their flocks by the strictest standards. Each farm carefully selects sheep breeds based on production goals. Merinos produce ultra-fine fiber for premium clothing, while Romney or Corriedale breeds generate longer, stronger fibers for industrial use. Every sheep gets a personal tag, recording age, health, and wool quality. Flocks graze on rotational plots, preventing soil depletion and preserving the land's fertility. Their diet is supplemented with hay, grain, and minerals to grow dense, uniform, and lustrous wool. Pens stay dry and well ventilated to prevent parasites and skin diseases. Each season, farmers vaccinate, deworm, and inspect every animal because a sheep's health directly determines fiber quality. Before breeding season, sheep undergo a process known as flushing. Their diet gets enriched with special supplements for several weeks to boost fertility and produce stronger lambs with finer fleece. During lambing, mothers are closely monitored so newborns get milk right away. A few weeks later, the young ones are tagged, weighed, and moved to lush pastures for weaning. When the warm months arrive, flocks are washed, treated for ticks, and left to air dry naturally before shearing. Each sheep is handled gently to avoid stress and yield a single clean fleece without tears. After shearing, they're inspected again. Minor cuts are treated and they're given time to rest before heading back to the fields. Every stage, from nutrition to shearing, follows strict animal welfare standards because only healthy sheep can produce the clean, durable wool of highest value. After months of care, when the sheep's fleece has fully grown back and the weather starts warming up, shearing season arrives. The timing's perfect. Sheep stay comfortable after losing their warm coat, and they've got plenty of time to grow a new one before winter hits. Before the process begins, the flock's kept in clean, dry pens and given lighter feed portions to keep the animals calm. Shearers are highly skilled professionals trained to work safely with each animal. They use precision electric clippers with fine blades, moving in a specific sequence, starting with the belly and legs, then working their way to the sides, shoulders, and back. The goal? Remove the entire fleece in one smooth, continuous motion without damaging the fibers. An experienced shearer can process 200 to 250 sheep in a single day, spending just 1 to 2 minutes on each animal. Short, dirty wool from the belly and legs gets separated for lower quality products, while the long, fine white fleece from the back and sides is reserved for premium fabric production. After shearing, sheep are checked for cuts or scrapes, treated with antiseptic, and sent to rest in wind-protected pens. Each large fleece, the result of an entire year of care and growth, now becomes the very first raw material in wool's industrial journey. From the shearing sheds, fresh fleeces head straight to the sorting zone, where human expertise remains irreplaceable, even amid modern automation. Each fleece gets laid out on wide tables and examined for color, fiber length, and fineness. Any sections tangled with grass, dirt, or too short for spinning get removed. Experienced sorters divide the fleece by zones. Wool from the belly and legs is reserved for industrial use, while the long, clean fibers from the back and sides are set aside for fine fabrics. This meticulous stage not only maximizes the value of each fleece, but also ensures consistency in production batches before the wool is compressed into bales and shipped to the washing plant. Once the sorting process is complete, clean fleeces are collected and moved to the pressing area. Here, powerful hydraulic presses compress each batch into dense rectangular bales, weighing between 300 and 400 pounds, tightly wrapped in burlap or heavy plastic for moisture protection. Each bale is marked with detailed information, including the farm of origin, sheep breed, and wool grade, ensuring full traceability throughout the supply chain. At the raw material processing plant, the wool bales are unpacked and evenly distributed onto conveyor belts for cleaning. The first stage happens inside an opener, a machine equipped with several rows of high-speed rotating metal teeth designed to separate tangled fibers and remove trapped contaminants like dust, grass, and dirt. This loosens the wool and prepares it to better absorb water in the next washing stage. The washing system consists of 6 continuous tanks of hot water, operating at temperatures between 168 and 180 degrees Fahrenheit. The first 3 contain diluted soapy solution to dissolve lanolin, the natural oil secreted by sheep that protects their fleece from moisture. The remaining 3 are filled with clean water for thorough rinsing. Water is filtered and circulated in counterflow through automatic pumps, conserving energy and maintaining consistent quality across all batches. Between each tank, soft press rollers gently squeeze out dirty water without damaging the fibers. Temperature and flow sensors automatically adjust washing parameters to keep the system at optimal safe levels. The extracted lanolin is collected and refined separately for use in cosmetics and pharmaceuticals. Finally, the clean wool enters a rotary drum dryer, where warm air circulates evenly as the drums continuously rotate, allowing heat to penetrate every strand. When the process is complete, the fibers reach a standard moisture level of around 12%, soft, vibrant, and completely free of contaminants, ready for storage and quality control. The dried wool bales are fed into a fiber blending machine. Each batch, varying in color, fineness, or origin, is precisely weighed and blended by rotating rollers with spiral blades that separate fibers clumped together during drying. A spray system maintains air humidity and prevents static, while sensors monitor speed for perfect uniformity. The fibers emerge soft, light, and springy, ready for the next mechanical stage. Entering the structural formation phase, the dried wool is fed into the carding section, where loose fibers are aligned in a single uniform direction. The material passes through a carding machine equipped with multiple metal-toothed rollers rotating at different speeds to create controlled friction and pulling force. Through this continuous motion, tangled fibers separate, straighten, and gradually clean themselves. Throughout the entire process, dust removal systems and electronic sensors eliminate short fibers, fine dust, and contaminants left over from previous cleaning stages. When the material exits the chamber, it emerges as a thin, continuous web of fibers, which automatically coils into soft slivers of consistent thickness and weight. After the carding stage is complete, the long and cleaned wool slivers move to the spinning section, a critical phase that determines the strength and fineness of the material. Here, the fibers enter a multi-roller spinning frame, where each roller spins at slightly different speeds to apply gradual drafting tension. The front rollers hold the fiber steady, while the back rollers accelerate slightly, drawing the sliver thinner while maintaining its elasticity and internal cohesion. Before the twisting unit, the surface of each strand is coated with an ultra-thin layer of spinning oil, reducing friction and preventing static buildup. As the fibers pass through the central twisting unit, they bind tightly together into a single strand, forming a structure that's both strong and elastic. The degree of twist is controlled by tension sensors, ensuring perfect consistency along the entire length of the yarn. The finished threads are wound onto large spools, then rewound into smaller, standard-size bobbins. Optical scanners inspect every strand in real time, detecting thick spots, weak points, or over-twisted sections. Any defects are automatically cut and joined using thermal welding, creating smooth, seamless connections almost invisible to the naked eye. In the next stage of production, the wool threads, now refined to the perfect balance of fineness and strength, enter the weaving system, where the material transforms from loose threads into a unified textile structure. And just like that, having traveled from vast pastures through washing, carding, spinning, and weaving, ordinary sheep's wool becomes the foundation for warm sweaters, elegant coats, and luxurious blankets that keep millions of people around the world cozy.
Every year, aircraft around the world cover more than 25 billion miles. That's roughly 26,000 trips around the Earth. And it's all thanks to the heart of aviation, the turbofan engine. Inside, there's a genuine inferno where temperatures reach over 1,100 degrees Celsius. But how can a machine made of metal survive where steel melts? How do they craft blades with micron-level precision that spin faster than a bullet? And why are some components today literally grown from powder using lasers? Stay with me till the end, and you'll discover a secret that'll forever change how you think about engineering. Turbofan engines that power the giants of the sky, Boeing and Airbus aircraft, seem like something out of science fiction. Yet they're the genuine embodiment of engineering brilliance. How do you assemble these remarkable machines from tens of thousands of parts and materials like pieces of a puzzle? Ordinary metals simply won't do for their manufacture. The engine must operate in conditions where temperatures can exceed 1,100 degrees Celsius. It's a proper inferno, and ordinary steel simply wouldn't cope. This is where titanium alloys enter the picture. Lightweight, robust, and capable of resisting melting in extreme heat. And for the hottest zones of the engine, they use nickel-based superalloys. Such extreme temperatures arise from the fuel combustion process in the combustion chamber. During engine operation, aviation fuel, typically kerosene, mixes with air and ignites, creating hot gases. These gases literally accelerate to extraordinary speeds and temperatures, over 1,100 degrees Celsius, sometimes reaching 1,500 in modern engines. This level of heat is essential to achieve maximum efficient thrust. That is, the hotter and faster the gases, the stronger the energy flow that drives the turbine and propels the aircraft. Here lies the principal challenge. The engine must not only withstand these extreme conditions, but also operate reliably. You know what's remarkable about the engine manufacturing process? Even individual components, such as turbine blades, are crafted with micron-level precision. For instance, blades are cast in a vacuum to ensure there isn't even the slightest crack inside. Some are formed to have a single crystal structure, meaning the metal has not a single seam. But that's not all. Three-dimensional printing? Yes, that's used too. For instance, for complex components that are impossible to create through traditional casting. Turbine blades are the engine's heart. They operate in the hottest zone and convert the energy from hot gases into rotational movement. First, a blade model is created from wax. Then the show begins. In a special furnace, superalloys are melted, composed of nickel, chromium, and other metals capable of withstanding temperatures above 1,100 degrees. This molten metal is poured into a ceramic mold. But the secret lies not only in the material, but also in how it's done. To ensure the blade withstands tremendous temperatures and stresses, it's often cast as a single crystal. This means the entire piece of metal has no seams or micro cracks. Why does this matter? Seams or micro cracks in such conditions are like a minefield. One error and the blade fails. Single crystals are grown through very gradual cooling. Once the metal cools, the ceramic mold is broken away and the blade undergoes thorough grinding. A special heat-resistant coating may be applied to the surface. And so, each blade is inspected individually. If there's even the slightest defect, it doesn't proceed further. Fuel injectors, combustion chamber components, or even compressor blades in aviation are manufactured using three-dimensional printing. For instance, GE Aviation prints injectors for their engines that weigh 25% less but are 5 times stronger than traditional ones. Layer by layer, from powder and light, components are created that allow aircraft to fly faster, further, and more efficiently. First, engineers create a digital three-dimensional model of the component with maximum precision. Here, every curved surface or cavity matters. Why? Because these components often operate in places where a millimeter can change everything, from engine efficiency to its reliability. Instead of the usual chunk of metal, they use ultrafine powder here, for instance from titanium, nickel, or Inconel. It resembles sand, but with particles so minute they're barely visible to the naked eye. The powder is poured into a special reservoir, and it becomes the building material. The printer's working principle is straightforward yet brilliant. It melts the powder using a laser or electron beam. The laser heats the powder to such a temperature that it literally fuses into a uniform metallic structure. Then the next layer of powder is applied and the process repeats. This method is called selective laser sintering or melting. And here's what's splendid. Three-dimensional printing allows the creation of even the most complex geometrical forms. For instance, components with internal cooling channels that simply cannot be manufactured through casting or milling. You see, in traditional manufacturing, you often need to create a large component first, then cut away everything superfluous. The resulting component isn't quite ready yet. After printing, it undergoes heat treatment, heated and gradually cooled to relieve internal stresses in the metal. Then comes final grinding, polishing, or mechanical processing if precision needs correcting. And naturally, each component passes rigorous testing. After all, this is serious business. If a component can't bear the load, the consequences could be catastrophic. Engine assembly takes place in an enormous hangar, where every square foot is occupied by tools, engine parts, and people in overalls. Everything begins with the engine casing, resembling a gigantic metal cylinder. This is the skeleton to which all other parts will be attached. The casing is crafted from titanium or nickel alloys, as it must withstand tremendous loads. Engineers work like watchmakers. The casing is secured in an enormous machine to ensure everything is absolutely straight. Next come the compressors, several rows of blades responsible for compressing air before feeding it into the combustion chamber. Blades are installed one after another. Each is inspected manually. Following the compressors comes the turbine stern. Next, the combustion chamber is installed, the engine's genuine inferno. Here, compressed air mixes with fuel and burns. Engineers install special injectors that ensure uniform fuel delivery. And here, everything must be perfect. An incorrect injector angle, and the engine could lose efficiency or even fail. Running through the entire engine is a central shaft, a sort of backbone. At one end of the shaft, the fan is mounted in the form of an enormous wheel at the engine's front, whilst at the other end sits the turbine. To install the shaft, they employ special robots. Once the engine's internal section is assembled, external systems are added. Fuel pipes delivering combustion to the combustion chamber. The oil system, ensuring lubrication of all moving parts. And electronics, because the engine is literally packed with sensors monitoring temperature, pressure, revolutions, and much more. These elements are secured using cables, tubes, and bolts that must withstand not only vibration, but also extreme temperatures. After assembly is completed, the engine isn't dispatched to an aircraft straight away. First, it's mounted to a test stand where real flight conditions are simulated. Once the engine passes all tests, it's disassembled, the principal components are inspected once more, and then it's assembled definitively. The finished engine is packaged and transported to a Boeing or Airbus factory where it becomes part of a new aircraft. So there you have it. Component by component, engineers create the aircraft's heart, capable of carrying thousands of passengers across continents. Isn't that a modern masterpiece? Do write and let me know if you'd like to see more videos like this.
Every year, people around the world devour over 50 billion pieces of fried chicken, millions of burgers, and a billion pizzas. But hardly anyone stops to think about what's behind those perfectly golden crusts and aromas we've come to take for granted. What if I told you that inside these flavor factories, technologies operate with more precision than surgical instruments, and recipes are guarded more closely than military secrets? In this video, you'll see how the food the entire planet loves is made, from KFC's secret blend of 11 herbs and spices to Domino's billion pizza assembly line. Stick around until the end, and you'll learn things they've never revealed, even in their advertising. Do you love KFC fried chicken as much as I do? Its story doesn't start in a fryer, but on massive American farms where chickens are raised under the strictest safety standards. After arriving at the plant, each bird flows through a cascade of automated systems. Artificial intelligence, like a vigilant guardian, analyzes images from high-resolution cameras, filtering out any defects. This isn't just a conveyor belt. This is a river of raw material flowing through an incredibly complex control system. Only the best specimens, passing this digital selection, move to the next stage. This is the first level of guarantee that every single piece will be perfect.
What follows is a processing stage that resembles a high-tech ballet. The carcasses are plunged into water at a precisely calibrated temperature of 140 degrees Fahrenheit to soften the feathers. Then, Automated machines equipped with thousands of rubber fingers spinning at tremendous speed strip away the plumage in seconds. These units can process up to 10,000 carcasses per hour. After that, laser-guided robotic cutters divide the carcasses into 9 standard parts with surgical precision, no more, no less. Every single piece gets weighed, scanned, and assigned its own digital footprint in the production management system.
But here's where things get really interesting. The chicken gets marinated in a special brine that makes the meat incredibly juicy. And then comes the sacred ritual, the breading. That legendary secret blend of 11 herbs and spices, a recipe Colonel Sanders developed way back in 1940, remains one of the most closely guarded trade secrets in the world. Word is, the original recipe sits in a vault at KFC headquarters. The blend ships to factories in 2 separate bags, and they only mix the contents right before breading. The breaded chicken gets fried in special pressure fryers at 375 degrees. It's that pressure that locks in the juiciness inside while creating that iconic crispy coating outside.
If beef's more your style, welcome to the world of the Big Mac. McDonald's uses only 100% beef from verified suppliers. After rigorous inspection, the meat's ground and formed into patties weighing exactly 1.6 ounces. This precision isn't a quirk, it's what guarantees each patty cooks perfectly. To preserve freshness without preservatives, the patties undergo flash freezing at 0 degrees Fahrenheit. This allows ice crystals to form instantly without damaging the meat structure. Big Mac buns are baked on automated lines, where the dough is mixed, shaped, and topped with exactly the amount of sesame seeds the standard requires.
Vegetables, crispy iceberg lettuce, onions, pickles, go through multiple rounds of washing and slicing. But the real secret of the Big Mac? That's the sauce. Its exact recipe is another mystery, guarded like classified intel. In restaurants, frozen patties get seared on a double-sided grill at 425 degrees for just 42 seconds. That's the perfect window. Golden crust on the outside, juicy meat inside. Then the crew, like soldiers on an assembly line, stacks the burger in strict order in mere seconds. That's why this icon of an era has stayed exactly the same for over 50 years. Did you know the Domino's pizza story started with a $500 debt? In 1962, 2 brothers bought a small pizzeria in the American town of Ypsilanti. Their main promise, which became the driving force of the entire industry, pizza delivery in 30 minutes. This rule sparked a revolution. Today, everything starts with the dough. At giant facilities, flour, water, yeast, and oil get mixed in industrial mixers. The dough rises in chambers with controlled humidity and temperature. Then it's divided into portions, shaped into round bases using presses, and flash frozen. That's what makes it possible to deliver identical dough to thousands of pizzerias around the world.
Tomato sauce is made from specially grown tomato varieties that get processed into puree within hours of harvest. Mozzarella is shredded on industrial graters, and pepperoni is sliced with laser precision. Sauce gets spread on the base,
Cheese is sprinkled on top, and exactly the number of pepperoni slices required by the standard gets laid out. Then the pizza heads into a conveyor oven at around 500 degrees Fahrenheit. Domino's Pizza is the world's largest pizza chain, cranking out roughly 1 billion pizzas every year. Their newest automated dough production center in Indiana can produce enough raw dough for tens of thousands of pizzas daily.
But how does all this food, produced in giant factories, make it to our table while staying fresh and flavorful? Behind it lies an invisible yet incredibly complex system, cold chain logistics. It's the actual nervous system of the global fast food empire. Frozen patties for the Big Mac and chicken for KFC travel in special refrigerated trucks where the temperature is maintained at -4 degrees Fahrenheit, accurate to within a degree. Sensors transmit temperature data to a central server in real time. Any deviation, the system sounds the alarm. Buns, vegetables, and sauces are transported in separate compartments at their own optimal temperatures. It's a whole science ensuring products don't thaw and refreeze, which destroys their texture and flavor.
Why does a Big Mac in Tokyo taste exactly like one in New York? The secret lies in sensory analysis science and obsessive consistency. Every major company has what are called sensory panels, teams of specially trained tasters with superhuman taste and smell. Their job? Sample products and compare them against the gold standard, a reference sample stored in the lab. They evaluate dozens of parameters: the saltiness of the sauce, the crunch of the lettuce, the softness of the bun, the aroma of the patty. Any deviation from the standard, even the slightest, and the entire batch can be rejected. It's a genuine flavor DNA code that companies replicate and reproduce worldwide. So no matter where you are, you always get that same familiar taste from childhood.
So, what's the main secret promised at the start? It's not 11 herbs and spices, and it's not some sauce recipe. The real secret these giants are hiding is creating consistency. It's psychology. The secret is they're not just selling food, they're selling comfort. In a world full of uncertainty, you always know exactly what your Big Mac or chicken wing will taste like. This isn't just lunch, it's an anchor of stability, a flavor that hasn't changed in years and decades. They took the most complex processes, from animal genetics to global logistics to flavor chemistry, and packaged them in a simple cardboard box. And they made us believe it's simple, fast, and always tastes the same. And that's their real genius.
Every year, the world produces over 4 million tons of hollow structural sections, and that's just in the US. Picture this, that's enough to build 400 Eiffel Towers annually. But behind these massive numbers lies the silence of steel giants we never see, because they're hidden inside buildings, bridges, and machines. How does rusty scrap metal transform into tubes capable of supporting the weight of entire bridges and weathering the storms of time? And what secret makes them both lightweight and incredibly strong? Stick around till the end, and you'll discover a secret you never knew existed. The market for hollow structural sections, where our heavy wall tubing reigns supreme, is a massive chunk of America's steel industry. Every year, the country cranks out over 4 million tons of these tubes. That number is mind-blowing. To put it in perspective, the entire Eiffel Tower weighs about 10,000 tons of steel. That means in a single year, American mills produce enough square and rectangular tubing to build 400 Eiffel Towers. It's an entire forest of steel giants sprouting up annually. We just don't see it because it's hidden inside structures.
Mountains of scrap metal, remnants of cars, construction frames, old machinery, sit waiting for their fiery rebirth. A giant crane with an electromagnet scoops up this metallic chunk and feeds it into an electric arc furnace.
Down there, in that roaring inferno where temperatures hit nearly 3,000 degrees Fahrenheit, this scrap metal transforms into a boiling, blinding lake of molten steel. Into this melt, like a chef adding spices, they introduce alloying elements, so the future pipe isn't just strong, it can withstand extreme loads and won't crack in freezing cold. Then this river of fire flows into a continuous casting machine, where it cools and solidifies, becoming long, massive steel billets. For our future pipe, these are typically thick, round slugs called blooms. Automatic cutters slice off pieces to the required length, and these hot but now solid cylinders are ready for the really interesting part. This is our blank, our solid chunk of metallic dough. But how do you make a hole in it when it's hard as rock?
To do this, it's sent to a heating furnace, where its temperature is brought back up to that perfect plastic state, 2,300 degrees Fahrenheit. And from there, glowing white hot with a blinding yellow radiance, it moves to the piercing mill. This is the heart of the entire process, and it's real industrial magic. Picture two massive barrel-like rolls spinning in the same direction. They're set at an angle to each other. The hot steel cylinder enters between them, and here's where something incredible happens. As they spin, the rolls don't just forcefully push the cylinder forward, they also make it rotate at a crazy speed. Because of this rotation and compression, enormous stresses build up right at the center of the metal cylinder, and the metal there literally loosens up, preparing to split. And at that exact moment, from the other side, a special piercing rod, or mandrel, is fed in to meet it.
It plunges into that loosened center like a knife through butter, literally punching straight through the solid billet, transforming it into a thick walled tube. It's an incredible sight. A solid chunk of metal becomes hollow in mere seconds, all happening with a roar and grinding that shakes the ground. The piercing process was invented in the late 19th century by the Mannesmann brothers in Germany and remains the primary method for producing seamless tubes to this day. But now we've got a round tube, and we need a square one. Our hot, freshly pierced tube immediately moves to the next stage, the forming mill. This is a series of roller pairs, but these ones aren't round. They have special grooves whose shape gradually transitions from round to square. The tube flies into the first pair of rollers, which squeeze it slightly from the sides.
Then it rotates 90 degrees and enters the next pair, which squeezes it from different sides. And so, step by step, passing through several of these gates, our round tube transforms right before your eyes into a perfectly square one. It's like a skilled sculptor, gradually, blow by blow, giving stone its desired shape. The final finishing rolls calibrate the tube with incredible precision, guaranteeing that all its walls have uniform thickness and all corners are perfectly square. The standard sizes are impressive. There are tubes with cross-sections of 500 by 500 millimeters. That's about 20 inches wide. And the wall thickness on these monsters can easily exceed 25 millimeters. Picture a steel wall as thick as a big encyclopedia. The weight of such a tube is simply colossal.
A single yard of this pipe can weigh over 800 pounds. That's like having 4 grown men standing on every yard of its length. And a standard 40-foot section? That'll clock in at over 10,000 pounds, the weight of 2 full-size SUVs, like a Range Rover. And that's just one piece. But here's the thing. Their real genius isn't the weight itself, but how intelligently it's distributed. That's their superpower. Picture a solid steel bar and a hollow pipe of the same weight. The pipe will be way more resistant to bending and twisting. Why? Because all the material sits on the outside, as far from the center as possible, and that's exactly where the greatest stresses hit under load. The hollow core? It just saves weight. Same principle as bird bones, hollow but incredibly strong.
That's why hollow profiles have the highest strength-to-weight ratio of any structural steel shape. This makes them the perfect choice when you need maximum rigidity without extra tons, in crane booms, heavy equipment frames, bridge trusses, and even roller coaster structures. It's because of these tubes that modern skyscrapers can withstand hurricane-force winds, and bridge structures last for decades, carrying millions of tons of cargo. From the final roller, a long, red-hot, now square tube emerges. It travels along a roller conveyor to a cooling table, where it slowly cools down, gaining its final, rock-solid strength. During cooling, the metal can warp slightly, so each tube is run through a straightening machine, a system of rollers that straightens it to perfectly linear precision. Now we've got a perfect, strong, but really long pipe. Time for the final operations. A massive saw roars to life and cuts it into standard lengths, say 20 or 40 feet. Each section goes through strict quality control. Specialists check its geometry, wall thickness, angle precision. Then they X-ray it with ultrasound to make sure there aren't any hidden internal defects. Modern flaw detectors can spot micro cracks smaller than a millimeter, invisible to the naked eye. Only then does the pipe get marked with all its info: steel grade, dimensions, batch number, production date. The finished, inspected pipes get bundled by robotic cranes, strapped down with heavy steel bands, and shipped off to the warehouse. And just like that, traveling from rusty scrap metal through the fiery heart of the furnace, surviving brutal piercing and precise forming, this humble yet incredibly strong steel rectangle emerges, ready to become the silent but reliable backbone for humanity's most ambitious creations. From the skyscrapers of Dubai to the bridges of San Francisco, from oil rigs in the North Sea to the frameworks of space launch pads, everywhere these unsung heroes of modern civilization are hard at work. They don't demand applause, they don't seek recognition, but it's on their steel shoulders that our world stands. And now you know their story. From fire to structure, from the chaos of scrap metal to the mathematical precision of engineering calculations. This is the real magic of industry.